Okay, welcome to Wednesday, December 9. And we have our last two topics of the semester today. And we're going to scan our website just quickly to make sure we're all on the same page. Some more colored pens out. Okay. So just website, we are at the bottom of the course. We're at the last week of the course. And I pumped that up for you. And last time we talked about roots of complex numbers and introduced polar coordinates. I'll go over those quickly again here, but I want to show you some very beautiful equations that you can graph with polar coordinates. So a little bit of fun. It's like half work, half fun. And then next week, as you know, just like your first exam is dedicated to your second exam, and just run through the procedure again. Monday, you come to work with your questions, whatever questions you want to review, but I'm not going to make special review questions for you. You can come to that session or not, as you like, but bring questions you want to practice or review, things that are you're not certain of or you just want to double check. Tuesday, you'll hand in your last XYZ homework. There's no written homework due next week. You handed in your last written homework last night. But you have 3 sections left to do at XYZ. That's by Tuesday night at 11:59. And then by that time, somewhere between 11:30 and 11:59 on Tuesday night, I will release exam 2. I'm on the week 16 webpage right here, so I'll release exam 2 right here on the week 16 webpage. And you have 48 hours to do exam 2, just like exam 1, and then you submit it to the assignments folder by 11:59 p.m. on Thursday, December 17th. It should be similar in length to the first exam. So whatever time you budgeted for the first exam, think about budgeting a similar time, make sure you got safety region in there. Make sure you're budgeting a similar time for the second exam. Okay, that is it. That is the course. After that, when all of your papers are graded and I've got your last grade report, I'll update those in your Google folder. And then I'll send an email out like exams are graded, your graded exams and your last grade report are in the Google Drive folder if you want to download them. Make sure you download those things if you want, because I'm not going to keep them any particular time. So I need to clear out that folder and start working with another group of students next semester. So make sure you take your papers out of that folder if you want them. What else do I want to share here? I am going to do some polar graphs with you, and that's a different kind of graph paper in a way. And so I provide some graph paper for you on my website. I was looking around this morning. I said, I've never made polar graph paper. I think I should make some polar graph paper for people. Well, yes, I should, but I don't have it right now. So I just want to say that if you went searching for polar graph paper online, you would find plenty. But I'm going to recommend one to you because I don't want you just going through the, virus sites, free online graph paper from Incompetech, whatever Incompetech is. Printablepaper.net. I looked at that. No, I didn't trust that website. But here's a website from, must be a math instructor at another school, called Graph Paper. And I'll send you the link in the chat window. I'll post the link to this graph paper in the chat window. And when you follow that link, he's just got a very simple page where he's got different square graph paper, polar graph paper, some other fancier graph paper. But polar graph paper looks like this. It's kind of a very broad, detailed, circular grid. And I'll show you how to use that today. Here's one with very dense lines. Here's one with even more dense lines. I printed some out so we could draw on it today. And then here's some combined with a little bit gentler, not so dense lines. Here's a polar graph paper. Here's a Cartesian graph paper. So I think a lot of people are thinking similarly to me, like, well, you don't have a space to run out and buy graph paper. And in particular, you can't go to Staples and find polar graph paper, probably. I guess I never looked. Staples, Walmart, whatever. So I'm just going to give you these links so you could print out some polar graph paper if you wanted. What I'll do is link you to this person's website and put this in the chat. But you're welcome to use any polar graph paper, but sometimes when people are desperate looking for free things, that's when you get the malware installed. Okay, so there in our chat is a link to that graph paper. Davidson is a, oh, I'd have to investigate who this person is, but looks like a fair website that's not trying to throw malware at you. Okay, so I'm going to close that and close those. Yeah, close those kind of. I like that one. I'll keep that one around. Okay, going to get out of there. Back to our website. So you know what we're doing for this last 3 meetings that we're having. And then let's get to work. Let's make sure I got this paper pinned right here. This is exactly what we're going to do. So first, remember what polar coordinates are. And we introduced that last time. If I have a point out here, and this point, let's just pick a big simple point to begin with. You know, x comma y is 3 comma 3. X-axis, y-axis. And by this scale, you might think every box is 1 unit, but remember, it's polite to tell people exactly what your scale is. So I'll toss a little scale on here. So I can think of that point as 3 points over, 3 units over, and 3 units up. That's a +3 and a +3. But I could also think of that point as 3√2 units away from the origin if I use my knowledge of the triangle to compute the radius, the hypotenuse. It's a 45, 45, 90 triangle. So I multiply the short sides by √2. I get the longer side, the hypotenuse. Now, there are a lot of points that are that far away from the origin. Here's another. Here's another. Here's another. You know, just symmetrically placed. In fact, there's a whole circle full of points. A circle with a radius of 3√2. So just telling you that the point is 3√2 away from the origin doesn't help you at all unless I also tell you the angle. And the angle here is 45 degrees. So once I specify the distance from the origin and the angle you should turn, do you see that I've also directed you to that point? I could use radians or degrees. I want to be open-minded when I do that, although most often in graphing, I'm using radians. In the book here, He's graphing some of these pictures with you in radians, some in degrees. I don't mind using degrees. If I was using radians, I would have called that point 3 root 2 pi over 4. Oops, got another person in the room. Got it. Now, the only trick about this is these are called polar coordinates. The only thing you have to be careful when you talk about polar coordinates is you know from your knowledge of trigonometry that 45 degrees is not the only way to describe this angle. So I could have equally well said 3 over root 2 and 360 plus 45, which is 405 degrees. Or 3 over root 2 and 2 pi plus pi over 4, which is 9 pi over 4. Those things would both be equal to 3 over root 2 and 45 degrees. Now, even worse, or even more offensive, it seems to people, is I could remove the restriction that radius was always positive. In other words, what if I told you to turn 225 degrees and then walk backwards 3 over root 2 steps? Wouldn't I land at that same point? So think about turning 225 degrees and then walking backwards 3 times root 2 steps, minus 3 root 2. And sometimes you like hesitate to write this, but there's a reason we need to write this, because in the back of your mind, you're getting a little nervous. Am I calling that radius negative? I thought he told me that radius is never negative. Well, that's true. Radius of a circle is never negative. So I want you to think of that minus sign in this sense. The radius is still 3 root 2. The distance is still 3 root 2 from the origin. But the minus sign is an instruction for you to walk backwards, to turn that angle, and then walk backwards 3 root 2 steps. So if you're willing to read that in that way, then I will allow you to write the radius is minus 3 root 2. And call that 3 root 2 walking backwards. That doesn't sound very mathematical, but it's at least understandable, kind of understandable. Now, what's the value of these polar coordinates, and what can you do with them? Let's look at a simple graph, and maybe the simplest graph I can. What would you do if you graph things not based on x and y, but based on radius and theta? I mean, you're used to graphing things y equals x squared. Oh, that's a parabola. Y equals 2x minus 3. Oh, that's a line. Even y equals x squared plus y squared is 4. Now that's a circle, but it's expressed in rectangular coordinates, or some people call them Cartesian coordinates. But what if I remove this limitation that you have to talk about X and Y? What if I allowed you to graph things based on R and theta? R equals 2. You know, x squared plus y squared equals 4 is just a circle of radius 2. So if I collected all the points that were 2 units away from the origin, I would be collecting a circle. If I graphed every point that had a radius of 2, I'd be graphing a circle. I'd be graphing the same circle. Could I graph a polar coordinate parabola? Could I graph a polar coordinate line? Well, yes, I could, but I was perfectly happy with the graphs of those things in rectangular coordinates. What if I wanted to graph different things? I want to graph things with circular symmetry. Austin chimes in the suggestion walking backwards or reverse steps. I like that too. You can think like that if you like. But what kinds of new graphs could I make if I used polar graph paper? If I used R and theta instead of X and Y? So I'm interested in, now these two correspond, but I'm interested in wholly different things. Like what would I get if I graphed R equals 3 sine theta? What would I get if I graphed R equals sine of 2 theta? Let's look at these 3 graphs on a single piece of graph paper. And I'm going to graph these things by graphing, just like I graph in X and Y. When I graph in rectangular coordinates, I have to create pairs X and Y. When I graph in polar coordinates, I have to create pairs R and theta. So this is graphing in polar coordinates. And these will be my first 3 examples. I'm going to get a sheet of polar graph paper, and I'm going to get a mellow large scale sheet first. And this will be the next paper in our handouts today. So I'm going to draw on this, and I'm going to draw 3 curves. I'm going to draw R equals 2, that's black. Colors do not always show up excellently on your screen, but I'm going to try it this time. I'm going to graph in green R equals 3 sine theta. And I'm going to graph in red R equals sine of 2 theta. That doesn't show up too badly in the camera. Before I do that, let's notice the difference between these 3 graphs. This first graph right here, I don't even talk about theta. It's like theta wasn't there. If I say theta isn't there, it's like saying I can let theta be anything I please as long as R equals 2. And that's what I'm about to draw. But first, let's get oriented on this graph paper. So the nice thing right here is they've set this up with the famous angles for us. I'm going to call this horizontal angle 0 degrees. Call this 90 degrees up here. Let's call this 180 degrees. And sliding down to the bottom of the paper, the bottom must be 270 degrees. But even between that, and I don't think I'll name every angle, or maybe I might for a short time, halfway between 0 and 90 would be 45 degrees. And then, do you see they split 45 degrees up into 3 pieces? Oh my gosh. This is the first time someone else besides me is referred to 15 degrees. 15, 30, 45, that makes the next one 60. And it makes the next one 75. So I know in some sense, every trigonometry class makes you think about 90-degree angles, 30-degree, 45-degree, 60-degree angles. Not every trig class makes you focus on 15 degrees or 75 degrees. So I respect that you guys have been flexible with that. And I'm not going to necessarily need to use them here, but I just want you to see that that's what a 15-degree angle looks like. Now let's collect this figure with different r's and thetas. And I could start with theta equals 0 degrees and r equals 2. In fact, that's the instructions. The only instructions in this equation are make r 2. Well, I'll put a dot. Now, I could also name these lines right here. I think I will name them generously. Let's call this 1, 2, 3. So I got room for a half mark. This represents 1 unit, 2 units, and 3 units from the origin. But you see the nice thing about the polar graph paper is I see this 1 unit all the way around. Makes it easier for me to draw. So let's go with my black ink and put a dot when r is 2 and theta is 0. But then I could put a dot when r is 90. I'm sorry, when theta is 90 and r is 2. That'd be up here. How about theta equals 180 and r is 2? This is not a hard table to make because it's very boring. Theta can be anything I please. R is always 2. Sorry, over here. And that's 2 units. I turned 180 degrees and then I went out 2 units. So I'm still calling this mark 2. I don't call that mark -1. That's -1 on the x-axis. It's 2 on the radial axis. And 2 down here. Now that's just 4 points at the corners of a circle. Of course it's a circle, but let's fill in. And I don't want to write 15 different angles here. So I'm just going to fill in dots that are 2 units away at every single angle on this grid. I may mean to my calculator do some calculations later, but not on this one. This is just a circle of radius 2. And I'm just tracing the over circle that's already there. Okay, so far so good. Black ink, not a problem. Now let's look at this green one, 3 sine theta. Now, sorry, move up to there. I'll rewrite a table down at the bottom of the paper. Now, when I change theta, I do change r. So I could think of my knowledge of a regular sine wave. Think of your knowledge of an ordinary sine wave from 0 to 360 degrees. I'll make a little chart down here. What does the sine wave do at 180 degrees? A sine wave looks like this. This point is a height of 1 at 90 degrees. This point is a height of -1 at 270 degrees. But this is in rectangular land. This is a graph of 3 sine theta that I ordinarily draw. Sorry, 3 sine theta that I ordinarily draw. This has height 3 if I multiply by 3, 3 and minus 3. How do I translate it to this circle? I think what I want to do is kind of zoom out on my paper. And I think I can do that, but I'm going to have to jiggle the camera for a second. So patience. You got a short tour of the basement there. Let me see if I can zoom out and give you a slightly better picture. And still kind of keep the camera flat. My camera is an old iPhone SE, not the fancier new ones. There's a really, really old one that you can get at Walmart reconditioned for $70. If they still have old ones that old. Okay, now I gotta reset the camera so that it's horizontal, no problem. And now we're back. I didn't gain much, but I gained a little. How could I realize this sine wave that I'm used to on this polar graph paper? Let's just start picking off points, and we're gonna make them green. When I'm at 0 degrees, I am at 0 height or 0 radius. 0 degrees, 0 radius. That put me dead center in the circle. When I'm at 90 degrees, I go 3 steps from the origin. 90 degrees up here. 3 steps from the origin is the outer part of this circle as I've marked the scale. Then I'm at 180 degrees and I'm back to 0. Okay. Then I go 270 degrees and I take 3 steps backward. 1, 2, 3. Okay, I just reproduced that point. Now I go 360 degrees back to where I started, and I go 0 steps forward.